Hi everybody, Physics Ninja here. Today what I want to do is look at transverse waves on a string. What we're going to do is grab the string. It has some tension in it and it has a certain size. We're going to wiggle our hands up and down in order to create a traveling wave on that string. There are many things that I want to do to describe the wave. First of all, I'm going to show you the expression to describe a wave traveling on a string. We're going to use that expression to learn how to calculate different quantities associated with waves. For example, what is the amplitude of the wave? What is the frequency, the wavelength, the period, the wave number, the angular frequency, and so forth? How do you use this information, for example, to calculate how fast the wave is moving, right? The speed of the wave. And maybe we can use some of these quantities to help us understand what the tension is in the string. I'm also going to show you how to calculate, for example, the velocity of any little segment of rope. Every little segment of rope on a transverse wave simply moves up and down. It has a vertical velocity that depends on its position and on the time. It also has an acceleration. At some point it's going up, it's going down, it's changing directions. So there is an acceleration associated with this. And given any kind of general expression for a wave traveling on a string, I want you to be able to calculate the direction that this wave is moving, right? We should be able to just look at the expression and determine whether it's moving to the right or to the left. All right, after the tutorial, what we're going to do is I'm going to give you two problems to work on. All right, we'll first read the problem and then I want you to work it out for yourself. Make sure you understand how to do it. Then you can watch the solution. All right, so two problems. Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. All right, so this is what we're going to do. Consider a string here where there is a tension in that string. The tension force is given by Ft. Now that string has a mass and it has a total length L. I'm first going to simply define something called the linear mass density. Okay, so it's mass density. And we call it linear because we're simply dealing basically in one dimension over here. The mass density is simply the total mass of the string divided by its total length. Okay, this is going to be an important quantity that we're going to use in a little bit. Now, when you grab a string like this and have a tension T in it and you start moving your hand up and down, you're going to create waves, okay? And those waves are going to propagate along the string, and the waves are, in this case, going to move to the right like this. Okay, and they're going to move at a speed v. Now, if you apply Newton's second law to any little segment of rope here, what you would find is something called a wave equation. And I'm not going to derive that in this video here. That's not the purpose of it. We simply want to look at solutions to this wave equation. But this is what the wave equation looks like. It says that any element of string at a position y, so y is the vertical displacement, x is the horizontal position. If you take the second derivative of that displacement with respect to its position, it's equal to this. It's 1 divided by v squared, and v is the speed of the wave, okay, how fast it travels along that string. The second term here is the second time derivative of the displacement. Well, what does this second term look like? This here simply looks like an acceleration term, right? A second derivative with respect to time looks like an acceleration. And you can derive this using basically Newton's second law of motion, F equals to ma. All right, we'll save that for another video. What's important actually is solutions to this equation. So for a solution, there are many types of solutions to this wave equation. Today we're focusing on transverse waves that travel along the string. And the solutions for transverse waves look like this. I'm just simply going to write it down. There's an A in the front. This is something we're going to call the amplitude. And the rest looks something like this. Kx plus or minus, I could have either a positive or negative depending if I'm describing a wave traveling to the right or to the left, multiplied by omega t. All right, this is a general solution to this wave equation, and you can verify that pretty straightforward, okay? All you'd have to do is take the second derivative with respect to time, substitute it in for the acceleration, take the second derivative of this solution with respect to position, you substitute it over here, and you're going to find that this satisfies this wave equation above as long as my speed is given by a very important expression, which is omega divided by k. If I satisfy this, I will actually find that this wave equation is satisfied by this. Now let's look at some of these various terms. Okay, what does this mean? What does this number mean? And this number? And how that's related to quantities such as wavelength, frequency, and period. All right, the number in the front is something called A. We call this the amplitude of the wave. Okay, the amplitude is simply referred to as the maximum displacement of the wave, right? That's the maximum value that you're going to move here. This is, for example, the value A. Now notice it goes from the equilibrium position to the maximum value. It's not going from peak to peak. Okay, so be a little bit careful with that. Next term is K. K is something that is defined as the wave number. Now that seems to be a little bit odd. It comes in units of radians per meter. Okay, and the reason that it's important for us is that it is related to the wavelength. Right, the wavelength is something you can measure on a string. Right, if I do one complete cycle, this distance here is something we refer to as the wavelength. Well, this wave number is related to that. It's simply 2 pi divided by lambda, our wavelength. So that means if you know the value k, you automatically know the wavelength. The next term is this omega. Omega is referred to as the angular frequency. Well, let's clean that up a little bit. And again, the angular frequency is related to the regular frequency or the linear frequency in hertz, right? And the simple expression that links both of those is 2 pi f. So that means if you know the value of omega, you automatically know the value of the frequency, because the frequency is simply 2 pi divided by omega. All right, great. And now look what happens. If we know both of these numbers, k and omega, you automatically know the speed of the wave. Okay, now the speed of the wave, now if we use our simple expressions, remember the omega I just told you was 2 pi f, and what else? Well, k, our wave number, was equal to 2 pi divided by lambda. So 2 pi divided by lambda, well, something like this. The 2 pi's cancel out, and what you're left with here is a very important expression. So you can calculate the speed of the wave if you know either omega and k, or if you know the frequency and the wavelength. Okay, so I'm just going to write this as a very, very kind of important expression, that the speed of the wave is given by this quantity. All right, I just want to say something else about the speed of the wave, which is very, very important. Okay, if you went through and you actually derived this by looking at a little bit of rope and you apply Newton's second law to it, what you would find is that the speed of the wave, okay, what you would get would be this expression right here. It would depend on the tension, and it would depend on the mass density of the string. Now this here equals to lambda f. Okay, we have two expressions to calculate waves on a string. Now one important thing is that the speed of the wave v in general, it doesn't depend on the frequency. Okay, be very, very careful with this, because this expression might tend you to believe that. Doesn't depend on frequency. This is really one of the key points. You decide the frequency, right? You pick f. You decide how fast am I going to move my hand up and down like this. Okay, the speed of the wave really depends on two things, right? Properties of the media. In this case, are properties of the string, right? Look at these properties. This is the tension force, right? How tight is the rope? And this is the mass density, which tells you how thick or thin the rope is, okay? And it also depends on the type of wave. So in this case here, it is a transverse wave, and this is related to the interactions in the string. Okay, so these are the two things that affect the speed of the wave. The frequency doesn't affect the speed of the wave. So even if you move your hand faster or slower, the speed does not depend on f. Okay, and that's a very, very important point. All right, sometimes you're also asked to describe the velocity of any specific point on the string. For example, at this purple point here, you may be asked, what is the velocity at a specific time for this point? Well, this point is described by having a particular coordinate x, and at any time I should be able to know what is the velocity and what is the acceleration of that point. This here tells me the position in the vertical direction, right? So how would you get the velocity of that point? Well, the velocity in that vertical direction, what you have to do is you have to differentiate the displacement in that direction, the position in that direction. So all you end up doing here is you take the derivative with respect to time. Okay, so if I differentiate a sine function, what I end up getting is a cosine function. So you're going to get plus or minus a. There's going to be an omega that comes out here, and here it's going to be cosine of kx plus or minus omega t. All right, what about the acceleration now? Well, the acceleration at any specific point is simply taking the derivative of the velocity with respect to time. Now notice this velocity also is different from the speed, right? The speed is how the wave propagates to the right or to the left. The velocity is really the vertical component here of the motion, okay? So to get the acceleration, you simply differentiate the above expression with respect to time. Now be a little bit careful here. If I have a cos function, I differentiate that with respect to time. I'm going to get minus sine. So you're going to get minus and plus a omega sine. There's going to be another omega that comes out if you apply the chain rule here. Kx plus or minus omega t. And here I've kept it general. Sometimes the wave is described by having a positive sign here. Sometimes it's described by having a negative sign there. All right, but all you have to do is apply our definitions for velocity and acceleration, and you should be able to obtain expressions for those. Now all you have to do is substitute the values in here, right? For any position x and for any time t, you can tell me exactly where every segment of the rope is, what its velocity is in the vertical direction, and what its acceleration is in the vertical direction. All right, now I want to look at the direction of propagation here. So again, let's consider first the case where I have a positive value here for the omega t term, okay? What we're going to do first is plot it at time 0, right? So if you have it at time 0, what you do is you simply substitute time 0 in there. So you're going to get a sine of kx. That's it. That's easy to do. Okay. The next thing you do now is you make this term small, right? If you remember from math class, what you end up doing here, this is a shift property, right? If I add or I subtract a value, I will shift the function either to the right or to the left, right? So there's two options. So left or to the right. Okay, so we're going to take our sine function. Let me just do a quick sketch of sine as a function of position x. Looks like this, right? This is x and this is the y position. This is at t equals to 0. Okay, now we want to know whether or not we shift it to the left or to the right. And the rule from math class, if you remember, if this term was positive, okay, if it was positive, what you end up doing is you shift it to the left, okay, if it's a positive term. If it's a negative term, you end up shifting it to the right as time goes on. So really, if I replot this curve with a little bit of time, right? I make time pretty small. What I'm going to do now is I'm going to shift it to the left. So all of these points move this way, okay? So the curve would simply look the exact same. I'm going to try to do a good job of it here. It's just the sketch. Oh, that lost it there. But that's all we do is we're going to shift it this side to the left if that's positive. Okay. If it were negative, then you would shift it in the opposite direction. Let me show you a little bit of that using Desmos for this case. All right, time equals to 0. Here we have our sine function. It has an amplitude of 0.8, as you can see from the expression up here. And now what I'm going to do is I'm going to add a positive value to it. Okay, in this case, I'm going to add positive 1. So it should shift everything to the left, right? So let's go have a look. This will be a blue curve, and there it is, right? It's the same amplitude. We've simply shifted the curve. Now let me increase that term a little bit more. This would be the omega t, right? So it's kind of like making time bigger. Look, I'll make the next curve in green. Shift it a little bit more now, 1.5 from the red one. You could see it moved a little bit further right to the left. So again, if you have a positive sign, that means that this wave here would propagate to the left in this case. All right, now if you consider the opposite case now, if I had a negative value here for this omega t term, again, this here in math class, if you remember, would produce a shift of that function. And since it's negative, you would shift everything to the right-hand side. So you first plot the wave at time equals to 0. That's the black line. And now at some subsequent time, the wave moves, all right? And it moves to the right, okay? And the bigger you make that term, the farther to the right I would have to plot this red curve. Okay. All right. So we've seen enough now. It's time to work on some problems related to transverse waves on a string. We have 2 problems for you. Good luck with them. Okay. All right. Here's problem 1. We have a transverse harmonic wave travels on a string according to this expression. So the y displacement as a function of its x coordinate and time is given by this expression. The mass density of this rope is given by mu, which is equal to 0.1 kilograms per meter. All right, we have a series of questions here. What is the amplitude, the frequency, the wavelength, the speed of the wave? What's the tension in the rope? At this specific position and this specific time, what's the velocity of the rope? At this same position and time, what's the acceleration of the rope? And in what direction is the wave traveling? All right, pause the video, try this problem out for yourself, and come back and watch the rest of the solution. All right, here's problem 1. We have a transverse harmonic wave travels on a string according to this expression. So the y displacement as a function of its x coordinate and time is given by this expression. The mass density of this rope is given by mu, which is equal to 0.1 kilograms per meter. All right, we have a series of questions here. What is the amplitude, the frequency, the wavelength, the speed of the wave? What's the tension in the rope? At this specific position and this specific time, what's the velocity of the rope? At this same position and time, what's the acceleration of the rope? And in what direction is the wave traveling? All right, pause the video, try this problem out for yourself, and come back and watch the rest of the solution. All right, remember now, this solution here has a general form, which I typically write like this. A multiplied by sine. The number in front of the x value is k. X, then plus the number in front of the time coordinate is omega. Okay, this is a general definition for a traveling wave on a string. So this helps us solve it, because right away I can see that the amplitude is simply the number in the front. Okay, that's this guy right here. All right, so my amplitude for question A, the amplitude is simply 0.17. Say that's given in meters. That's pretty straightforward. All right, question B says, what is the frequency? Okay, how do I find the frequency? Well, again, if you're given this general expression, the number that multiplies time is something called the angular frequency. All right, so we already know that omega is equal to 17.1, and that is measured in radians per second. Now we're looking for the linear frequency f measured in hertz. But there is a simple expression that links both of those. It's 2 pi times f. So if you know omega, you automatically know the frequency of oscillation. All you need to do is take this omega and divide it by 2 pi. So here we go, 17.1 divided by 2 pi. Lo and behold, put that in the calculator and you should get, say, 2.72. That is measured in hertz. All right, great job. Let's keep on going. Let me just box these up. We've got our first 2 solutions here for the first 2 problems. All right, what do we want in part C? Part C says, what is the wavelength? All right, let me just go over here. I have a little bit of space. We're looking for the wavelength lambda of this wave. Now, the number that multiplies the x coordinate here is something called our wave number. And the wave number k is related to the wavelength. The expression is 2 pi divided by the wavelength. So all you have to do is simply rearrange this. That means that the wavelength then is going to be 2 pi divided by that wave number. So now we substitute the expression because the wave number is right here. This is 2.4. So we have 2 pi divided by 2.4. Put that one in the calculator and you're going to have a wavelength equal to 2.6 meters. All right, great job. Let's look at the next one. What is the speed of this wave traveling on the string? All right, to get the speed, what we're going to do here, this is problem D. To get the speed V, we have to simply remember that the speed is given by the wavelength multiplied by the frequency. You can also write this in terms of omega, the angular frequency, and the wave number of the wave. In that case, it ends up being the ratio of those two values. So let's just use the first expression here. We just calculated our wavelength. This was 2.6 meters. And the frequency, we had a 2.72 hertz. So that means that our speed of this wave, calculating that, I get approximately 7.1 meters per second. All right, great. Part E says, what is the tension in the string? All right, so if we have a speed equal to this and a mass density, now the speed of that wave is actually given by the properties of this string. It's how much tension there is divided by what is this mass density. All right, so we know, think about what we know here. We know the mass density, that's 0.1. I know the speed, I just calculated that. We should simply be able to isolate to get the tension, all right, which I'm writing as, now be careful here. Let me just write Ft, just so we know it's the force of due to the tension. Now, we simply have to isolate. What we're going to do is square both sides. So you get V squared is simply equal to the tension force divided by mass density. All right, so my last expression now is the tension force is given by V squared multiplied by mu. So now we substitute our numbers. You get 7.1 squared. Our mass density was 0.1. And now we get our tension force, which is approximately 5.04. And that should be measured in newtons. All right, great job. Let's go look now at the next problem. All right, problem F says, at this specific position and that time, what is the velocity of the rope? And we're looking at just a small segment of rope, and we're really looking at the vertical velocity as a function of position and time. This here, this expression gives me the displacement. So what you have to do is you have to differentiate this with respect to time. If I take the derivative of this with respect to time, again, if you remember the general expression, there's an omega that will come out of the expression. So you're going to have A omega, and the sign switches to cos of kx plus omega t. All right, now we simply substitute in all our values. All right, so that vertical velocity at this position, 3.3, and at that time, so we substitute. So the amplitude was 0.17. My omega value is 17.1. And now cosine, this term here is exactly the same, right? You get 2.4 for the wave number, except the x value that we're looking at now is this value. It's 3.3. And then plus 17.1 is my omega, and I want to evaluate this at exactly 0.46 seconds. Now remember to keep in mind that everything here has to be in radians, okay? Otherwise you're going to get the wrong answer when you use your calculator. All right, so that vertical velocity then ends up being minus 2.9 meters per second. All right, the last part here, G says, what is the acceleration of the rope at this exact time? So again, if you're given the velocity expression right here, right, or in terms of all the variables here, if we want to know the acceleration of that specific segment of rope, again, at this position x and at that time t, what you have to do is you have to differentiate the velocity with respect to time. So if I differentiate the velocity here, I'm going to get an omega that comes out again. I'm going to get A omega squared. Now it will be minus because if I differentiate a cos function, it becomes minus sine and then kx plus omega t. All right, again, all you have to do now is substitute in all the numbers in here. So it's quite a lot of work here. So we have minus, our amplitude was 0.17. Our omega is 17.1, and you have to square that expression right there. Now what else? Now sine of this exact same term as up above, right? 2.4 multiplied by 3.3. 17.1, and we're evaluating that at a time of 0.46. Let me just write that at the bottom here. I'm running out of space. All right, you put that in the calculator, and lo and behold, you should get 3.9 meters per second squared. That is for that vertical acceleration of that segment of rope at that time. All right, the last problem says, in what direction is this wave traveling? In order to see that, what I'm going to do here is I'm going to first plot the wave at time equals to 0. So I've substituted time equals to 0 right here. And then what I'm going to do, then I'll plot it at other times. I'm going to substitute different values of t here. And I'm going to do that using a slider so we can see how the wave moves. So the software that I'm going to use here is going to be Desmos. So let me open up that window right here. All right, so let me get rid of the blue line first. So we have the red line, which is at time equals to 0. See, the amplitude is 0.17. You can see the wavelength is 2.6 meters that we calculated before. And now over it, I am going to, let's set that slider equals to 0 right here. And I am going to just plot a blue line right over it. That's the same thing. Now look what happens over here. When I start increasing time, I'm going to just move the slider a little bit. Look, when time is 0.02, you can see that the curve over here, the blue curve, shifted to the left. Let's move it a little bit more. At 0.04, it shifts a little bit more, and so forth, right? It will keep moving to the left this wave as time progresses. All right, so let's go back to our window. So that means that this guy here moves to the left. All right, this makes a lot of sense. If you remember from a math class, whenever you add a term like this to a function, what you're going to do is, if the term is positive, like it is in this case, it means you move it to the left, right? If this term is a negative term, then that would mean you move it to the right, right? It becomes a translation to the right. In this case, it's a translation to the left side. All right, so that's it for this problem. All right, here's problem 2. We have a transverse harmonic wave travels on a rope according to this expression over here. Here are the questions I have for you. What is the frequency, wavelength, and the period of the wave? What's the speed of this wave? What's the maximum displacement at any point on the rope? What's the maximum speed at any point on the rope? And what is the direction of, what direction is this wave traveling, to the right or to the left? All right, so pause this video, try to answer these questions, then come back and watch the rest of my solution. All right, first question, what is the frequency of this wave? Well, again, we know right away by looking at this expression up here, you should know right away that the angular frequency is whatever multiplies the time. So in this case, it's 3.5, and that is measured in radians per second. Same thing as before, omega is linked to that frequency of oscillation, right? So now you just do a little bit of algebra, omega divided by 2 pi, and that's it, you're off to the races. So we get 3.5 divided by 2 pi. You put that in a calculator and you should get 0.56 hertz. All right, great. B, what is, oh, sorry, we're still at A. I'm jumping right ahead of myself. What is the wavelength? Okay, the wavelength again. Well, if you know the number that multiplies my x coordinate right here, that means that you know the wave number. The wave number in this case is 2.2, and that is measured in radians per meter. Okay, so, and it's also linked to the wavelength. It's 2 pi divided by lambda. So lambda then is simply 2 pi divided by that wave number, which is 2 pi divided by 2.2. We put that in the calculator and we should get a wavelength that is approximately, say, 2.86 meters. All right, next one, what is the period of the wave? The period of the wave is how long does it take one segment to do one full cycle? Again, that's a simple definition. It's simply 1 divided by the frequency. So it's 1 divided by 0.56, the number we already solved for. I put that in the calculator. You should get, again, approximately 1.79 seconds, or 1.8 seconds. Close enough for me. All right, problem B. Problem B now says, what is the speed of this wave? Super easy. If you know the wavelength and you know the frequency, you automatically know the speed of the wave. We know the wavelength we calculated was 2.86. Our frequency was 0.56. So that means that the speed of this wave should be approximately 1.6 meters per second. Question C says, what is the maximum displacement? So again, the max displacement, they're really looking for the maximum value of y. Again, that is by definition, it is the amplitude of the wave. Right? The amplitude of the wave for this case here is simply the number that multiplies the front is 0.03 meters. That's it. That's all. Okay? Remember that the sine function, any trig function, sine or cos, is simply going to go between -1 and 1, right? So think about the maximum value is 1 for this function. So you multiply that number by the number in the front, you're going to get the amplitude right here. All right. D says, what is the maximum speed at any point on the rope? Okay. Again, each point on the rope moves up and down. The velocity of any point on the rope in that vertical direction here is simply going to be, you got to differentiate this. So again, I'm going to assume a general form here of kx minus omega t for that displacement. So if I take the derivative of that displacement with respect to time, again, so that derivative, you're going to have a minus omega that pops out. Okay. And now the sine converts to cos when you take the derivative with respect to time, and you're left with simply this, right? You're simply using the chain rule here in order to find that velocity. Now the question asks specifically for the maximum speed. So again, the maximum speed is simply the number that multiplies everything, right? Because here we are left with cosine is a function that goes between -1 and 1. Right? So if I wanted to find the maximum of Vy, it's simply going to be this number right here. Okay? So Vy max, simply the amplitude of that velocity here. And that is omega simply times a. You don't have to worry about the negative. I'm looking for the speed, which is a scalar value. Okay? Now we substitute our values. So our omega, we know it's simply the number that multiplies time. 3.5, that's the omega. The amplitude we just calculated, 0.03 meters. All right, we put that in the calculator, you should get about 0.105 meters per second. Okay, I'll maybe just round that to 0.11. Close enough. All right, for part E, it says, in what direction is the wave traveling? Again, I kind of like to do it like this. First, I plot it at time 0. Okay, at time 0, the expression is 0.03 sine of simply 2.2 times x. You don't have to worry about this term at time 0. Okay, if you make a sketch of this, think about what happens over here. This is time. This is y. Let's just do it in black over here. This is going to look like a simple sinusoidal function. And I can continue over here on this side as well. All right, what we know about this is that this amplitude right here is 0.03. All right, now let's go to a different color. Let's go to blue, for example. Now I'm going to add the other term that depends on time, right? So now the more general expression is 0.03. So it's going to have the same amplitude. We have sine of 2.2x. And then minus 3.5t. So imagine there is a small value of time. Look what happens to this term over here, right? This is a shift, right? This is a shift in either the left direction or the right direction, right? But if you remember from math, if you have a function and you apply a minus shift to the argument here of the function, what that does is if it's negative, negative means it shifts everything to the right. Okay, so let me go ahead and trace it. So that means that this point gets shifted a little bit when time goes on. The top point gets shifted a little bit. So now the wave simply looks like this at a small value of time later. This is for small t. Let me go ahead and trace it a little bit on this side. Oh, it's a little bit tricky here. Got to be careful. All right. So when you have a negative value over here, you're going to shift to the right side. That means that the direction of travel of this wave here is going to be in this direction at the speed v that we calculated in the second part. Okay. Again, you can use Desmos if you wanted to show that. But again, if you have a positive wave number and a negative value for the second term, what you're going to do is you're going to shift that function to the right-hand side.